In this lesson, we're going to look at measures of variation in data sets. So as we've seen already, we've studied measures of center for data sets, such as the mean, or median, or the mode. Well, they only describe the center, a measure of center of a particular data set. Now that's valuable, but it doesn't tell us anything about the spread or variation in our data set. So for example, if you had a nature guide that told you that a river that you had to cross has an average depth of 3 feet, would you want to just jump in and start wading across without additional information? Well, no, that wouldn't be a good idea, because some parts of the river might be very shallow, only 1 foot, but other parts might be very deep, like 7 or 8 feet. So the average might be 3 foot, but you still wouldn't be able to get across just by wading. So you would make sure you'd want to be able to swim. So you need some type of measure of variation for data sets. Another reason for studying the dispersion or variation in a set of data is to compare the variation between 2 or more distributions. It's very important when you have distributions to understand variation in them. This is a very important concept in quality control in many different industries. For example, let's take a look at this problem. Suppose that we have 2 banks, the Jefferson Valley Bank and the Bank of Providence, and they've taken a small sample of the waiting times of their customers. So here we have the Jefferson Valley Bank and the Bank of Providence data, and the Jefferson Valley Bank, these times are in minutes down here, so the customers waited on average 6.5, or not on average, but the sample, we had customers who waited 6.5, 6.6, 6.7, up to 7.7 minutes. And then the Bank of Providence, one customer 4.2 minutes, 5.4, up to 10 minutes. Now, for these 2 data sets, let's evaluate the mean, median, and mode for each set, and that'll give us an understanding of why we really need a measure of variation to properly describe these data sets. So, jumping to Excel. So here we have the waiting time for each bank listed in a spreadsheet. So here's the waiting times for the Bank of Providence, the Jefferson Valley Bank, and here are the waiting times for the Bank of Providence. Now, if we take the mean for each one, we see that we will get 7.15 for both. So right here is the formula for evaluating the mean. Remember, it is we just use the average function, and over here is the same for the Bank of Providence. So we see that we get the same number. The median, we can quickly look at that and evaluate it. The median here, we've got 10 values here, and so the median is going to be the average of the 6th and 7th data value. You see 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5, and so we're going to have to take the average of the 1, 2, 3, 4, 5th and 6th data value, these 2 right here. So the score right in the middle of those is going to be our median, and that's going to be 7.2 in this case. Now for the Bank of Providence, and let's also note the mode here is 7.7 for the Jefferson Valley Bank. Now for the Bank of Providence, the median would be the average of these 2 numbers, the 2 middle numbers here, and that's also going to be 7.2. And the mode will be 7.7 as well. We can see that the mode is the score that occurs most frequently, that is 7.7. Just like over here, it is 7.7. There. Now, so we have our measures of center for both data sets being exactly the same. However, do these data sets really look the same? No, they do not, right? it appears that the Bank of Providence has much more variation in its waiting times than the Jefferson Valley Bank. And generally, in industry, you want to try to reduce variation in products that you're producing. Even waiting times. It's not really a product that's being produced, but the Jefferson Valley Bank, if you think about it, you walk into a bank and you see that some people are, if you were to see that some people were getting served very quickly and others, and you maybe took a long time, you might be a little frustrated. However, over here, if you go into the Jefferson Valley Bank and you see everybody's waiting about the same length of time, you don't have to worry about jumping around trying to find the shortest line. You might be less frustrated. So generally speaking, variation oftentimes want to be minimized. We want to minimize that in industry. So obviously a measure of center isn't really properly describing the difference between these two data sets. So we need some type of measure of variation. Well, there are several ways we could try to do it. We could try looking at the range of each data set. That would just be the high score minus the low score. Well, that's generally a very poor measure of variation for data sets. It sort of works in this case because for the Bank of Providence, our range would be 10 minus 4.2, so that would be 5.8. And our range over here would be 7.7 minus 6.5, or 1.2. And well, we do see that the range for the Bank of Providence is larger, but oftentimes you'll have outliers in your data set, and the range is generally a very poor measure of variation. So it is not used very often at all. You might think then, well, what if we did this? Suppose we were to take the average of the distance that each score is from the mean of the data set. What I mean by that is the following. Suppose we, let's just draw a picture here. Suppose we have a data set where we have the mean, like right there, and suppose we have a score like x1 here, maybe x2 is over here, x3, and perhaps x4 is here. And we want to get a measure of variation for this. Oops, x3 right there. Well, what you might try to do is you might try to average the distance that each score is from the mean. So you might try to do this. You might add up x1 minus the mean. So you add up all of these distances between each data value and this number, the mean, and then you take the average, so you would divide that by however many data values you have. Well, that's a valid attempt. However, you see the problem is this. Some of these numbers are positive, like this number would be positive because x1 is larger than x bar, but this number right here, x2 minus x bar, would be negative. This number would be positive, and this number would be negative. So you see, you're going to get cancellation. And in fact, it is a fact that this is always equal to 0. The numerator will always be 0 because you'll always have this cancellation, and you're always going to get 0 for this. So this is not going to work. So what are we going to do? Well, you might say, well, perhaps we could, if this is negative, why don't we take its absolute value of all these numbers? Then we won't get cancellation. Well, that's a valid attempt. So what you're trying to do is this. By the way, as far as notation goes, notice that what we have written here is, we could denote this as the summation of xi minus x bar divided by the number of scores that we have. So that's what we have written right here. However, as we've just said, this always comes out to be 0 because you have cancellation with these terms. So you might say, well, perhaps we could do this. What if we tried taking the absolute value? So suppose we did this. Well, that's okay. That actually would work and give you a reasonable measure of variation. However, it doesn't really mesh very well with math theorems that we're going to see coming up later on. So it certainly isn't bad. It's certainly better than the range, but we don't use this very often because it doesn't mesh well with other theorems that are going to be coming down the road. So what we actually do is this. We actually take each of these values and we actually square them like this. Okay. Now, by squaring them, you see all of these terms up here, if we were to square them, then they would all be positive and we wouldn't get any cancellation. And then you can think, this isn't really correct, but you can think of and then taking the square root like this to, in some sense, take into account the square. But remember, if you have a squared plus b squared, I don't want you to think this. This is not a plus b. That's not equal to a plus b. The square root and these squares here don't cancel each other because you're adding these two terms here. If you were multiplying them, then okay, but you're adding them, so this is not true. But in some sense, we can think of this square root as sort of counteracting those squares, and that actually is a very good measure of variation. It meshes very well with theorems that we will deal with later on. Now, the only issue here is that, as we'll see, this n down here, normally coming from a sample, we usually want to divide by n minus 1 when our data comes from a sampling. Now, if it comes from a population, if we have every value in our population, then we would divide by n. Okay, but coming from a sample, you divide by n minus 1. And when you do that, what we have here is what we call our sample standard deviation. Standard deviation. I'll just write it as SD for standard deviation. And we usually denote that with the letter S, like this. Now, if it comes from a population, we would change the n minus 1 to n and denote it by the Greek symbol sigma. So we have this stated in the definition in the next slide. Let's take a look at that. So here's what we're going to use as a measure of variation. So let's take a look at our definition here on our slide, and then we'll come back to these two data sets and calculate the sample standard deviation for each. So here are all of the formulas that we're going to be using for our population and sample standard deviation, and also variance. I didn't talk about that, but here it is. So for our population standard deviation, we define it to be this quantity right here. So we use the Greek symbol sigma, and it is simply the square root of the summation of each score minus the mean squared, and then we divide that by the number of observations in our population, or the number of scores in our population. The variance is defined to be sigma squared, so notice if we square both sides here, if we take each side here and we square it, we obtain this equation up here, and then sigma squared is called your population variance. So if you calculate a variance and then take the square root of that number, you get your standard deviation. Now for a sample standard deviation. Down here is our formula. So you simply sum up the difference between each score and the mean squared, and you divide by n minus 1. There's a good mathematical reason why we want to divide by n minus 1 instead of n when we do a sample, but it's sort of beyond the scope of this course to really go into those mathematical details. And also notice we have what's called a sample variance. If we were to square both sides here, we obtain what's called our sample variance. Notice for some notation here, notice for the mean right here we use an x bar instead of a mu. That's standard notation for a sample mean versus a population mean. And we replace the sigma with an s when we're dealing with the sample standard deviation. Now, before we go back to that Bank of Providence data, let's look at an example where we do this by hand so you know how to do that. And I'll also show you how to plug it into a calculator like a TI-83 and evaluate the standard deviation. So let's take a look at this example. So here we're given a sampling of hourly wages for some part-time employees at Home Depot. So we have $12, $20, $16, $18, and $19. That's a very small sampling of just 5 people. Let's calculate the sample variance and the sample standard deviation. Alright, well the first thing you need to do is to calculate the mean. So now if you calculate that out, you'll see that's 17. Of course, you just have to add these together and divide by 5. You will get 17. Now, to evaluate the sample variance, we have to add up the difference between each score and the sample mean, square it, and then divide that quantity by n minus 1. So that's what we have written down here. So now evaluate that on your calculator and show that you get 10. Notice what we did here. We have 12 minus 17 and then we square it. So we take that number, subtract 17, square it. Take 20, subtract 17 and square it. Take 16, subtract 17 and square it. And so on until the end. Now notice that we're dividing by 4 because n is equal to 5 in this case. So of course n minus 1 is going to be 4. Alright, now evaluate that on your calculator and verify that you can get 10. You should do that by hand. Now when you do that on your calculator, make sure you use parentheses correctly. When you enter this into your calculator, you're going to have to enter it as parenthesis and then parenthesis 12 minus 17 squared. Of course, you could easily do that in your head if you wanted, you know. Of course, that's negative 5 squared. But sometimes the data values are not so easy to subtract in your head. And then 20 minus 17 squared. So this is how you would have to enter it. And then you'd go out to 19 minus 17 squared. Now you have to put parentheses around everything in the numerator, right? And then divide by 4 and verify that you get 10. Alright, now that is our sample variance is 10, so our standard deviation is then going to be the square root of this number, and so our sample standard deviation, S, is going to be the square root of 10, which is 3.16. Now, let me show you how to enter this data into your calculator and then get 3.16. And then we'll go back to the bank data and show you how to do it in Excel as well. So here we have my TI-83 emulator. Now to enter this data into a list, you see right there is our stat button with the word list right above it. Just click on that stat button and you'll come to a screen like this. Now we want to choose Edit to edit our list, so number 1, or highlight it and hit Enter. Now let's enter all of our data here into list 1. So we'll enter 12, 20, and there we go. Now let's go back to click on Stat again, so all of our data is now entered into list 1. So now click on Stat, and we're going to go down over to Calculate now. So move over to Calculate, and we want one variable statistics. So now select the number 1, either hit 1 or highlight 1 and hit Enter. Now we want to do one variable statistics on list 1. So you have to click second and then that list right there, and then select number 1, and you see now you get an L1 there. So once again, the way I did that was to click on second, the Stat button, and then select list 1. Now hit Enter. And here's all of the sample statistics for our data set. You see we have a mean of 17 right there. That's exactly what we had calculated. And we have a sample standard deviation. That's the S of x of 3.16. That's exactly what we have right here. That's the square root of 10. So right there, that's what we want. It also gives us the population standard deviation. That would be where we would divide by 5 right here instead of 4, but we don't want that because this is coming from a sample. And so there you go. That's how you can easily evaluate means and standard deviations using a calculator. You just have to enter your list of your data into one of the lists on your calculator and then do one variable statistics. Now let's go back to that bank data, and I'll show you how to do that in Excel as well. So here we are back at our bank data set, and we want to calculate the standard deviation. Well, it would be pretty cumbersome because this has 10 values in it. It would be pretty cumbersome to do that by hand. So we would either want to use a calculator. We could do this on the TI-83 pretty easily. We could put all this data into list 1 just like the previous example and put all this into list 2 and then calculate our mean and standard deviation for each. But let's try it with Excel for something different. It's good to know how to use Excel. So the standard deviation function goes like this. Equals, and then ST, type in STDEV, and you see you get some options here. There's STDEV.P. Now that's going to calculate the population standard deviation, where you divide by n. We want the sample standard deviation. Right there it is, STDEV.S. So that's the one we want. So we can type in STDEV.S, parenthesis. Now it's asking us for our data, so we can simply highlight this data like that. Notice how it puts B3 colon B12 in there, hit parenthesis, and there is our standard deviation, our sample standard deviation for the Jefferson Valley Bank data. Let's do the same thing over here for the Bank of Providence. So we could copy this over, put it right there, but let's do it by hand. So equals STDEV.S for a sample. Highlight our values here, close that off, and hit Enter. And there we go. So we see that our standard deviation for the Jefferson Valley Bank is 0.47, while as our standard deviation for the Bank of Providence is 1.82. So, and that's sort of what we expected. We would expect that the standard deviation for the Jefferson Valley Bank is smaller than the standard deviation for the Bank of Providence, because we can see there is less variation in this data than in this data. And so by stating the mean or the median and in conjunction with the standard deviation gives us a better way to compare two data sets.